Quantum computing could fundamentally disrupt the massive AI data center industry now being built around the world. Companies like Google, Microsoft, Amazon, Meta, IBM, and NVIDIA are investing billions in GPUs, giant data centers, cooling systems, and electricity infrastructure to power the AI boom. But there is a growing question behind all this spending. What if the computing architecture powering today's AI is not the one that dominates the next decade? Quantum computers work in a completely different way, and if they become commercially powerful sooner than expected, they could dramatically reduce the amount of classical computing needed for certain AI and optimization workloads. That could reshape the economics of data centers, energy demand, and the entire future of artificial intelligence. Before you imagine millions of quantum computers replacing every GPU overnight, that is not what is happening. Quantum computers are still experimental, expensive, and extremely difficult to build. They are not ready to replace ordinary data centers today, but something more important is happening. The question is no longer whether quantum computers will become useful, but when they will become useful enough to change the economics of computing. To understand why, look at the extraordinary scale of today's AI infrastructure boom. Companies like Microsoft, Meta, Google, and Amazon are investing billions in massive data centers packed with advanced GPUs to train and operate increasingly powerful AI models. But these facilities need far more than chips. They require buildings, cooling systems, networking equipment, transformers, transmission lines, and enormous amounts of electricity. The International Energy Agency has projected that global data center electricity consumption could exceed 1,000 terawatt-hours by 2026. Countries like Ireland are already dealing with data centers consuming a significant share of national electricity demand, while US utilities are preparing for huge increases in power requirements. And that creates a serious problem. Data centers can be built in years, but power infrastructure can take much longer. Grid connections, transmission lines, and new generation projects often require years of planning and construction. Communities are also pushing back over electricity use, water consumption, noise, land requirements, and infrastructure costs. This is where quantum computing enters the story. Traditional computers use bits, represented as zeros or ones. Modern AI relies heavily on massive numbers of classical computing operations performed by specialized processors such as GPUs. Quantum computers use qubits, which can exist in combinations of quantum states through superposition and can become entangled. But quantum computers are not simply faster versions of ordinary computers. They are designed to provide advantages for specific types of problems, including optimization, chemistry, logistics, finance, and scientific simulation. Imagine searching through billions of possible solutions to find the best one. Which delivery routes use the least fuel? Which molecules could become effective medicines? How should financial assets be distributed? These are exactly the kinds of difficult problems where quantum algorithms could eventually provide major advantages. And that is where the potential disruption begins. Quantum computing does not need to replace every GPU. If a relatively small quantum system can eventually solve a specialized problem that currently requires thousands of classical processors, companies may need far less hardware for that workload. The physical footprint could shrink. Electricity demand could shrink. Cooling requirements could shrink too. That does not mean data centers disappear. It means they evolve. The future is likely to be quantum plus classical. Classical computers will continue handling storage, networking, everyday workloads, and most conventional AI tasks, while quantum processors could act as specialized accelerators. Major technology companies are already preparing for this possibility. Google has demonstrated important milestones with its Willow processor. IBM continues developing larger quantum processors. Microsoft is pursuing topological qubits through its Majorana research, and NVIDIA is investing in quantum classical computing. But there is an important reality check. Quantum computing remains highly experimental. Qubits are fragile, errors are difficult to control, and reliable fault-tolerant systems remain a major engineering challenge. So whenever you hear that a quantum computer is thousands or millions of times faster, ask one question. Faster at what? The real breakthrough will come when quantum computers demonstrate repeatable, economically valuable advantages on problems businesses actually need to solve. And once that happens, the economics of AI infrastructure could change very quickly. A company planning to spend $5 billion on a classical facility may suddenly have to ask whether that building will remain competitive for the next 10 or 20 years. That uncertainty alone could change investment decisions before quantum computers ever become dominant, because markets move on expectations. If companies believe quantum computing is approaching commercial usefulness, they may build differently, spend differently, and design the next generation of data centers around a hybrid future. Energy is one of the biggest reasons quantum computing could transform AI infrastructure. Today's giant AI data centers consume enormous amounts of electricity, forcing utilities to expand power generation, transmission, and grid capacity. Quantum computers still require energy, especially for cooling and control, but if they can solve certain complex problems with far fewer physical operations, the energy needed for useful computation could eventually fall dramatically. That could reduce pressure on power grids and shrink the physical footprint of some computing workloads. But quantum computing also creates a major security challenge. Banks, governments, hospitals, companies, and consumers all depend on encryption to protect sensitive information. A sufficiently powerful, fault-tolerant quantum computer could eventually break some widely used encryption systems much more efficiently than classical computers. This is why cybersecurity experts are preparing for Q-Day, when quantum machines become capable of breaking current cryptographic protections. There is also a serious harvest now, decrypt later threat, where attackers collect encrypted data today and attempt to unlock it in the future. That makes post-quantum security an urgent priority. As for when quantum computing becomes commercially important, there is no guaranteed timeline. The most realistic path is gradual. Quantum machines will first tackle specialized scientific and optimization problems, then work alongside classical supercomputers, and eventually become useful for selected commercial workloads. When that happens, data centers will evolve rather than disappear, combining CPUs, GPUs, AI accelerators, quantum processors, storage, networking, and advanced cooling into hybrid computing facilities. And that is why the real story is bigger than quantum-killed AI data center. Quantum computing could challenge the assumption that today's AI infrastructure model will remain permanent. Right now, billions are being invested under the belief that more AI requires more GPUs, more buildings, and more electricity. But if quantum systems can eventually handle certain workloads using far fewer classical resources, the industry could shift from build more to compute smarter. That shift would create winners and losers. Companies with flexible infrastructure may adapt more easily, while those locked into one computing architecture could face greater risks. Chip manufacturers, cloud providers, data center operators, utilities, cybersecurity companies, and governments will all need to prepare. And quantum computing should not be seen as AI's enemy. It could become one of AI's most powerful partners. AI could help design and control quantum systems, while quantum processors could accelerate specialized AI workloads. Classical computers would still handle most everyday tasks. So the future is probably not quantum versus classical, it is quantum and classical working together. The AI data center boom is real, and so is the quantum revolution. The trillion-dollar question is not whether quantum computing will matter, but how quickly it becomes useful enough to change where the world invests its computing money. Quantum has not destroyed AI data centers, not yet, but it has placed a huge question mark over their future.